Okay, last time we talked about the rotating machine. The rotating machine is the machine that convert the energy in between mechanical and electrical. Mechanical and electrical. Right? And usually it converts into the rotating power. And the output power will be, in case of convert from electric as an input to mechanical power as an output. The output power will be calculated by P mechanic is the torque multiplied with the angular velocity, right? Torque is in Newton meter, and the angular velocity is will be in radian per second. In radian per second here. Okay. And for electrical power, we can measure the power input in kilowatt or in watt, right? Yes, right? In watt or kilowatt. Here is PE, right? And or PE can be calculated by for three-phase machine, right? For three-phase machine, it will be PE will be square root 3 into VI and power factor, right? Here, cos theta is power factor. For DC machine, PE will be V and I, right? V multiplied with I for DC machine. Okay, and usually when we measure the speed of the machine, right? The speed of the machine, speed of the machine, usually we measure in the term of RPM or round per minute. Round per minute. And for round per minute, we just say N, okay, NR, speed of the rotor. So we can convert this value into angular velocity in from round per minute. We can convert to radian per second. Okay, so the omega will be from round per minute. This would be round per minute, right? Into radian, round into radian, so multiply 2 pi, right? Per minute into per second, right? Per minute to per second divided by 60, right? We can convert by this formula, right? If we know the speed of the machine, right? Let's say, for example, 1000 RPM, we can convert this value into radian, how much the radian per second, right? And this is simple, right? We just convert before we calculate the mechanical power. And for the machine which convert the mechanical power to electrical power, we say we call this machine as the generator, right? Generator action. So the mechanical power as an input, the electrical power as an output. Okay, so so far we come to this knowledge. So you have any idea about efficiency of the machine? Efficiency, machine efficiency, right? Machine efficiency will be power output divided by power input into 100%, right? This is the efficiency of the machine. For motor, this will be mechanical power divided by electrical power, right? If we know the current and voltage, we can calculate electric power. And if we know mechanical power, or we can know the torque. If we know the torque and we know the speed, we can calculate the mechanical power. Then we can compute the efficiency of this motor, right? Similarly, for general action, we can compute power electrical as an output and mechanical power as an input. So, and we just substitute to this formula. We know the efficiency of the generator. Okay, just inverse to each other. For motor, mechanical to electrical is generator. Electrical to mechanical is the motor mode, right? So the machine can be worked in both modes, right? Motor and generator mode. Okay. So if you need to compute the efficiency, so it depends on the rotating machine is the motor or the generator. Okay. And for electrical power, you can use this formula, right? It depends on this is the AC three-phase machine or DC machine. But for mechanical power, you can use this formula for mechanical power, right? Torque multiplied with angular velocity. Okay, this is the basic knowledge of the general machinery, right? When we need to analyze about the machine efficiency. Okay. Now let's come to talk about the DC machine. Okay, direct current machine. For the direct current machine is that the machine that we we generate or we supply the DC voltage to those machines. Okay, and direct current machine can be both generator or motor. For generator, so we drive, right? We drive this machine by mechanical power. We drive by maybe by engine or by steam turbine, maybe hydro turbine. If we drive it, and we will get DC DC source. It will work as DC source, right? And for motor, we supply, right? We supply DC, right? Supply DC power, DC electric, and then we get the mechanical power, right? Is we rotate, right? We have the driver to drive mechanical load, right? We supply DC to this type of machine. So the structure of this machine will have two main parts, right? One is the rotor, which is we have the coil. This is the conductor in the coil, and another part is the stator. For the stator is the part that produces the magnetic field, right? Magnetic field. The magnetic field can be produced by permanent magnets, right? Permanent magnets, or we can use the coil, right? Electric field. If we this is not permanent magnets, we can use the field winding. We can use the field winding to produce, right? If you supply the current, right? As you know in the physics class, that if you supply the current, you have the electric field, right? In S with a right hand rule, right? Or right hand rule, you produce the magnetic field. So we can produce the magnetic field without permanent magnet, right? We can use the electric field, right, to produce the magnetic field. Okay. So we have two parts, rotor and stator, here for direct current machine. So this is the upper figure is the permanent magnet for DC machine, right? If we have the magnetic field from N to S here, right? If we drive this coil, right? We drive this coil, we'll get the voltage out from this coil. And when we have some circuit that moving and we need to connect it with, we would like to make the electrical connection. we need the device known as brush and commutator. Commutator is the ring, right? Ion ring here, right? Conductor in the ring shape, and the brush is the usually made by the carbon is touched on this ring, and this ring can move, right? During moving, the electrical can flow through this brush, right? We can have the electrical connection to the moving part of the machine, right? Because this is the carbon brush and slip ring or commutator here, right? So if we draw the symbol of this coil, we draw to this. Okay. And this is the moving coil, right? Moving coil here. Let's produce the torque or voltage here. And this is the commutator and carbon brush here. Okay. We can call this sometimes we call this winding as the armature conductor, armature winding. Armature winding. So this is armature winding. So if you drive the armature, you get voltage here. You drive with some force, right? If we give some force here, we get voltage out from the carbon brush. Okay, we get voltage here. Okay, or if we supply the voltage here, this will be the force to drive this armature winding. We supply. If we supply the DC source here, okay, we have that this part will be moved, right? We move like this. Okay. And in many cases, we don't use the permanent magnets because we cannot control the field of the magnetic, right? So a lot of DC machine will have the field winding. Field winding means the winding that produce the magnetic field, right? Here, the field winding will be in the stator. Stator means that it's non-moving part, right? Non-moving. So non-moving part we call stator winding here. So the current supply to this winding will produce the magnetic field, right? Instead of using constant permanent magnet. Okay, we call this winding as the field excitation or excitation field. Excitation winding or the current we call excitation current here. Okay, this field winding. So this part is in separate, right? In separate circuit. So this part we can use this symbol, right? We supply the DC source to the winding, right? And this source controlled by one can be controlled by one adjustable resistor. We can use adjustable resistor to control the current, right? Current, field current here, right? So this is just in separate circuit we can see. And if we draw the circuit to include the inductance, right, of this coil and the resistance of this coils will be in terms of RA and LA, right? This is the resistance of armature winding, and this is the conductance of armature winding right here, and this is the induced voltage here. This is the equivalent circuit, right? In fact, this is the coil, right? It's the coil with impedance, with resistance, with conductance, with inductance, and it also have the induced voltage inside this coil. But we cannot make the model in that term, right? So we need to write down the model in terms of resistance, right? In a connection with inductance, and then in a connection with one voltage, induced voltage, EAF, right? For induced voltage here. So this is the model of this coil, or this coil, right? Here. And for the excitation winding, we model by one coil, right, to produce the magnetic field here. Okay. So in motor mode, so we need DC supply here, right? And also we also need DC supply here. Okay, then we will get the P mechanic output for motor mode. Okay. In generator mode, we still need the field excitation, right? We need to supply field excitation, and then we drive this machine by mechanical power, right? We will get P out, right, as a voltage of this machine here, VA as a output. So the field excitation always need, right, when we operate this type of machine. For generator mode, we still need field excitation, right? But we have some cell excitation model that I will talk later. Okay, by connect this terminal to this terminal together. Okay, so in summarize, so we have the machine will have two parts, right? We have the armature winding like this. This is the armature coil, right? Armature coil. Armature coil may be L and R, RA and LA. Okay, RA. And then we will have field excitation, RF, right? LF. We have two winding. For DC machine, we will have two winding, at least two winding. So we can connect these two winding together. If we connect it in parallel, like this. For example, if we would like to operate as a motor and we supply the DC supply here, right? We have the current flow here. So this machine will move, right? Because we have both the current flow to armature, the current flow to produce the field excitation. So this machine will move. We call this machine as the shunt DC motor, shunt connection. Okay, and on the other hand, we can connect these two winding in series connection. We connect in series here, like this. It's connect in series, right? We will have the current flow to produce the field and the current flow to the armature. So this machine will move, right? And we call this connection a series connection. And sometimes we have more than one field winding. We can connect one as a shunt connection and another one for series connection. We call this type of machine as compound machine, right? Compound machine. To mix shunt and series machine together as a compound machine. Okay. Here, this is the configuration of the DC machine, right? So we have two winding. This is the field winding and armature winding, right? We can connect by shunt connection, right? As a parallel connecting, right? We make a parallel connection, right, of these two winding, right, for field winding and armature winding, right? So we call this is shunt connection. Or we can connect in series circuit, right? It's field and then armature winding. So this is a series connection, right? Or we have both series and shunt, right? With series and then shunt together. We call this is compound connection. Compound connection. This is we call this type of connection as short shunt. Short shunt means after series winding, the machine, the armature and the shunt is parallel together, right? And another compound connection we call long shunt compound. Long shunt means with the after series, right? After we make a series connection of in between series winding and the armature winding, then we connect this circuit in parallel with one shunt winding, right? We call this connection as a long shunt compound connection. So to solve this, to make analysis of this type of machine, there is the main variable is the voltage, right? The voltage at the terminal and the current, right? Current at the terminal, and then the current flow, right, into into the armature. The current flow to the field excitation and the flux produced, right, by the flux produced by the field excitation winding. So there is a few there may be few equation that you need to make understand and uh, use, right, of use, and how to solve, how to analyze this type of machine. So how much the power output when you supply this voltage, and how much the speed, how much the voltage you get when you drive this machine with this speed, for example, right? Okay, in DC machine, the field excitation provided the magnetizing current is occasionally provided by external source, right here, right? We can supply this is in separate. You can supply in separate, or you can make a connection and it use the same power supply, right? And here we call this is in separate. We call separate excite. Yeah. Separate excitation, and if you connect it together, even shunt, series, compound, if you connect the circuit together and you supply only one or you have only single one electrical terminal, right? We call this type of machine as a self excited machine, right? So that means we connect the field winding with armature winding. So we call this self excited machine. Okay, so we can analyze this machine, both self excited, separate excited. Okay. Okay, this is a different type of connection, right? It's depend on the objective that we use, right? For shunt machine, usually, okay, I will explain here, right? For DC shunt machine, usually we use this coil, this conductor with high resistance. So the current will flow to this part, not much, right? Not much. And we got the for motor mode. Usually we have the motor, DC motor, with almost constant speed. In this case, if we need constant speed, we use shunt connection. But for series connection, usually we use this is low resistance, right? Low resistance here, and then the current will flow to the same amount, right? And in this case, we will get a very high torque, right? If we want to use the high torque machine, but we don't need constant speed. We connect by series connection, right? High torque. Yeah. So we can merge this advantage of these two types. So both constant and high torque together to make a compound connection, right? The torque will be higher than shunt, and the speed will be more constant than series, right? So mixed together, and the performance in between shunt and series, right? We have uh, both type of field excitation right here on this type also. Okay. Okay, this is what I have explained. I think I have explained most on this slide already, right? Okay. Okay. Okay, now let's see the DC machine model, right? And uh, this is the force on the wire, right? If we would like to compute the force, right? The force F that make to the winding in the armature winding. The force is given by F is the current, right? And L cross vector to B. B is the magnetic flux density, right? ILB. F equal to ILB. I think IL and cross B, right, is the direction of the vector of the force, right? The magnetic field is flow to this way, and the force will be in the right hand rule, right? With the right hand rule, right? I L cross B, right? You may remember some, okay? Here is the force, right? And then if we compute in terms of torque, the torque will be torque for multiple coil will be KBI psi alpha. Right? Psi is the psi alpha means the angle in between B and normal plane of the coil, right? And usually psi alpha is close to 90 degree, right? We just consider most of the coil will be have this force, right? So sometimes this is go to 1, right? Go to 1. Okay. K is the constant depending on the coil geometry. It depends on how we develop this coil, right? How many number of turns, what is the angle. So for example, this is the shape of the coil, the number of turn, right? The angle of the coil, right? Is we represent by K constant, right? It depends on the machine constant. Okay. And B is the flux density caused by stator field. B is the flux that's produced by this magnetic field, right? This is B. Okay. Then usually gamma we say is close to 90 degrees. So psi gamma is equal to 1. Okay. And the power output is torque multiplied with omega, right? Power PM. Mechanical power. Not it may be input or output, but it's mechanical power, right? Mechanical power will be torque multiplied with omega, right? Yeah. And torque is K phi with current, right here. K phi with current here. With current IA, we substitute torque by KT phi and current IA. And then we know that from electrical side, the power will be V and I, right? Or maybe EB and IA. If we consider the energy in mechanical and electrical the same without loss, right? We neglect loss at this moment. We neglect loss. If there is no loss, this equal together, right? Equal together. IA will be cancelled to each other. Then the voltage induced inside the machine will be K phi omega. E is K phi omega. Ka is constant and the flux density, and the omega is the radian per second, right? The angular velocity. So if you drive the machine fast for DC machine, I think maybe next term you may have a chance uh, to do some laboratory. If you drive the machine faster, the voltage increase in DC generator in this case. And for motor, if you drive the motor with higher voltage, the speed will be increased for DC motor. So this you drive, the more speed, the voltage will increase, right? For for uh, for generator, if you use the DC machine as generator, if you drive it with higher speed, the voltage increase. You measure the voltage in the laboratory. So when you go for laboratory next term, so I suggest you to come back to see this this equation that will make you get more idea about this type of machine, about the DC machine. On the other hand, for motor, if you drive it with a higher voltage, the speed will be higher. Okay, speed will be higher. So anyway, it depends on the constant value and the excitation flux of this machine. Okay, and this voltage we call the back EMF voltage, electromotive force. EMF means electromotive force of this machine. Okay. Okay, EB is K phi omega. K is the armature constant, so K is the constant value. So if we know the constant of this machine, we can compute its performance. Okay, the voltage EB represents the counter voltage opposing the DC excitation, so we call back EMF, or we can call this as back EMF voltage. So, and in case of motor and the general voltage, in case this is the voltage, counter voltage in case of motor, and the voltage generated by this machine in case of generator. Okay, and the electric power dissipated or generated by this machine, the power will be P is EB multiplied with IA, right? As I write up here, right? EB multiplied IA. So it's, in this case we can say PE equal to PM only for the case that lossless machine, right? Lossless condition, or ideal. It's only in ideal, right? It's not in practice, right? In practice we cannot have any equipment without loss, right? Okay. And Ka can be obtained by this formula. It depends on the number of magnetic pole, right? K is number of magnetic pole, how many pole that we provide during we make a winding, and the number of conductor per coil, right? N here, P and N divided by 2 pi. M is the number of parallel part in armature winding. We can have a parallel circuit part in armature winding. So this is the K factor. Ka factor. Okay, then if the machine operates in generator mode, VA will be less than EB, right? VA less than EB, and the current will flow in this direction. No, this is a generator mode here. Generator mode here. VA is less than EB, and the current will flow out of the machine, right? So this is maybe you connect this machine to some load, right? To the load. The output is the electrical power, right? We use this is as generator here, IA. So EB is greater than VA. So, and in motor mode, the current we supply, right? We supply the voltage here, right? The voltage here, and VA must greater than EA, right? And the current will flow into the machine, right? And this is will be the output. Right? So for generator, this is will be the input, right? P mechanic will be the input. This is P mechanic. So, and this is this is a formula just for separate machine, right? Separate excite. So we need to supply another supply for field excitation. We need another supply, DC supply for field excitation for both motor mode and generator mode, right? Okay. Then for separate excite, the circuit is separate, so we can use the formula in separation. This is a field circuit, right? And this is a major circuit. Major circuit. Okay, this is a major circuit here. So field winding circuit is this circuit, right? This circuit. This circuit with KCL, we can say that VF and RF will be equal, right? VF equal to IF, RF, right? Or we can rearrange into this formula, okay, IF. And for this formula, for motor action, the current flow in this direction, right? Current flow to this machine. So by KVL, the equation will be VA equal to EB plus IARA, right? EB plus IARA. So we can rearrange into this equation. Okay, and for generator mode, for generator action, the current flow like this, and EB greater than EVA. So by KVL, the relation is EB equal to VA plus RAIA, right? And then we can rearrange into this formula. So this is the basic formula for DC machine, right? So if we know what we can measure in practice, we cannot measure EB, right? Because where is EB? EB is here. EB is here, right? Inside, right? Inside with behind the behind the resistor, right? Equivalent resistor is integrated into the resistor. It's not exist in practice, right? In practice, we can measure the terminal voltage of the equipment, right? So at the terminal, so at the connection, we can measure at the terminal. So we can measure VA, we can measure the current flow, right? The current we can measure, right? For example, if we have machine like this motor, we supply some, right? We supply plus, minus. This is VA, right? And this is the current, so we know IA. We know VA and IA, but we don't know EA, EB inside the machine. We cannot measure EB, right? So we have VA, IA, right? And if we know the machine well constant or specification, we know from the data sheets, or we measure the resistance of this machine, so we may know RA, right? Then if we measure IA, VA, RA is constant, right? So we can compute for EB, right? Then we can compute for EB. And when we know EB, we can compute. If we know the speed and EB and constant, we can compute the flux density, the flux of this machine also. And if we know the flux, we can compute the torque. So, the formula, the equation will relate to each other. So we can then we can get the other factor by after we measure V and I, and another factor we can measure in practice is the machine speed, right? The speed, and that we transfer into omega m. So then we know machine speed, we know machine voltage and current, right? Okay, this is just to give you some information that in practice, when the machine is not operated, the flux is not go to zero. There's some residual flux or residual magnetization here. It's not go to zero. So when the motor or the generator, DC motor, DC generator, there is some excess flux. After we operate, it's not go to zero. Okay. And it's not linear. EB and IF in practice is not in linear. It's not like this. It's not like this. It's not like this. So when we increase the current, right, and EB is changed, it depends on the specification of the machine. It's changed in accordance to this shape, right? S shape here. Okay, this is S shape. Because when the current increase to some value, the material here, the material become saturation is start to saturation. It's not will be like this shape. It starts saturation. It cannot increase the voltage anymore. Even we increase the current, right? We call this behavior of this phenomenon as the saturation in magnetic circuit. Okay. But anyway, if we know this graph, it depends on the material, right? If we know this graph, we can get the information. For example, if we measure the field current 1 ampere, it means that the back EMF voltage will be 100 volt, like this, right? So one machine, this is PM, right? We have two winding, right? This winding may be armature winding. This is field winding, right? We have VA and IA. So this winding we have VF and IF, right? This is going to field winding, and this is by slip ring and go to armature winding. This is a moving part, right? For armature, it's moving, and field winding is non-moving part, right? This is field. Okay, I think you get some idea, right? And if we measure the field current will affect to the voltage here. The field current, the higher field, the higher voltage, right? The higher field excitation, the higher voltage with this relation. It depends on the it's not always with this curve. This is just example, right? This is typical for example. Typical relation, right? For example only. It's not mean that all machine light will be use this curve. It's not like that. Okay. Okay. I think maybe we see this example and then we have some break. Okay, let's see. This is a separate exercise. DC generator. What mean by DC generator? DC generator is mean that we supply the field excitation, right? We supply the field excitation with some voltage, and then we drive this machine, right? And then we'll get the power output in electrical term. Okay. So we supply field excitation and we drive this by mechanical power. We will get electrical output. Okay, yeah. So in this case, if the prime mover is driving the generator at 800 round per minute RPM, round per minute. What is the no load terminal voltage VA? What is VA here, right? If we drive this by the omega is 800 round per minute, right? Per minute. Right? So let's see the information here, right? Okay. Generator magnet, we know the excitation. Okay. The generator excitation curve. We know the terminal voltage with no load and 1 to 5 with no load and with 1 ohm. The schematic generator rate that is 100 volt, 100 amp with 1000 round per minute. So in this case, the generator rating is 100 volt, right? And with 100 ampere. When we drive, it's by 1000 round per minute here. Okay. We drive this generator, but in this case, if we drive is by the speed only 800 round per minute, only 800 round per minute. Okay. So in this case, we first we compute for the field current first, right? So the circuit parameter RA is 0.14 ohm. Yeah. 0.14 ohm is RA is 0.14 ohm and VF is 100, RF is 100 ohm. Yeah, so in this case VF is 100 volt and RF is 100 ohm. So we can compute IF. IF is therefore IF with 100 volt and 100 ohm. The current will flow 1 ampere, right? V divided by R, right? 1 ampere in this case. 1 ampere is produced 100 volt, right? 100 volt. Yeah. At the speed 1000 RPM. So 1 ampere is here, right? For IF 1 ampere. So we know that EB will be 100 volt, right? Here. 100 volt at 1000 RPM, right? 100 volt, 100 amp at 1000 RPM. This will be there. So, but in the case of running at 80% speed, right? So we can assume the relation is linear. If we assume the relation is linear at 1000 round per minute, is produce 100 volt, right? With the same condition, right? Therefore, at 800 round per minute, so the voltage will be by linear relation, it should be 80 volt, right here. You can use this formula as well. This should be 80 volt. So we can see from this relation, right? Because if other is constant, right? The flux density is constant. If the speed and the voltage will have the linear relation to each other, right? If the speed is increased, the voltage is increased in this case. So we can use linear relation to assume the voltage, back EMF voltage. So in this case, with no load, right? Without any current, EB will be 80 volt, right? And the terminal voltage will be 80 volt also because no current flow. If we measure the voltage here in between the terminal, the current is 0, right? 0 into R, right? We get VA equal to EB, right? For open circuit, right? Without any current flow. Okay. And then how about if we connect 1 ohm with this terminal? What is the voltage here now? Because the induced voltage inside is 80 and this is 1 ohm and armature current is 1.14. Therefore, the current flow to this direction and we can compute VA, right? So the current will be 80 divided by, right, 2 resistors in series. This will be 0.14 plus 1 here, right? The current is here, right? It's 70.2 ampere. 70.2 ampere. And how much for the current? 70.2 ampere. How much the voltage across 1 ohm here? The voltage across 1 ohm will be current multiplied with resistor, right? This will be 70.2 volt. In this case, the answer will be 70.2 volt. So this is the answer of this example. Okay, I will give some break for you and we come back for this example. Okay, any question?